Dear friends, this is the second part of the video where we describe the impact of an asteroid on the Earth. In the previous section, we have studied the orbit determination of the body and its travel up to the atmosphere boundary. And now we see in detail what is happening soon after. And for doing that, we need to make some reference system changes and to take some assumption about the size and the material of the body itself. Let's start.
Hereby we have the resume of the old video's content, both the part 1 and the new part. I won't repeat here what has been treated in the first part, and we introduce the second part, which is also made by 3 steps. The first is the study of the trajectory within the atmosphere. Then we have the determination of the body motion, space versus time, and finally the simulation of a possible impact. We remember that the impact can never occur if the asteroid gets completely burnt. However, if the impact does occur, the body can either target the water or the land. In the second case, it will form a crater. We start from the parameters found in the part number 1. The body enters the atmosphere at a certain date, which is the sum of 8,213.49 days, that is the date when the body is hitting the sphere of influence of the Earth, plus 15.5 hours, altogether 8,215.6 days, which is the 28th of June 2022 at 14:09. That's the date when the body is entering the atmosphere. We know also the radius, that is the radius of the Earth plus 100 kilometers, the thickness of the atmosphere, and also we know the hyperbolic anomaly capital F3, describing the position of the body within the hyperbolic orbit. We have now to determine the polar coordinates. And first of all, we need the true anomaly F3, which can be determined by using the arctangent formula, by plugging in the value capital F3 found already. And to solve the sign ambiguity, we need to consider what was the true anomaly when the body enters the Earth orbit. And because it was negative 137 degrees, then we take the minus sign. And thanks to the polar coordinates R and F, by using the perifocal coordinates and the rotation matrix already introduced in the previous presentation, we get the state vectors R and V in the ECE coordinates. The ECE reference system is displayed on the right side, and on the table right up we have the values of the two found vectors. We need now to change the frame into another one, still centered on the Earth, but having z-axis oriented as the North Pole, that is the ECI, Earth-centered inertial. To change it, we need a rotation clockwise along x and about the inclination epsilon, that is 23.44 degrees. Last but not least, we need a further rotation along z-axis about the angle theta, that is the rotation made by the Earth from a reference time, the 1st January 2000, up to the actual Greenwich time. The rotation theta can be found by this simple linear formula, and if we eliminate the periods, we get 5,379 radians. This last reference system, ECEF, is not inertial any longer. It is rotating together with the Earth. With the found angle theta, we can build the last rotation matrix and change into the new reference system. By combining the two rotation metrics together, we get the new state vectors. Those are represented in the table aside. About the velocity, we are still not down, however. since our system is not any longer inertial. We have to consider that the Earth has a spin, and this is directed along zeta axis, and the draft speed is the cross product among the angular velocity of the Earth and the position vector. And this velocity is here represented in the brackets. The velocity in the new system is actually the difference between the absolute and the draft one. And the flight path angle is also, for definition, the angle between the two vectors r and v minus 90 degrees. And so it changes as well. Finally, we find the new values for velocity and gamma angle, slightly different from the ones in the inertial system. And now we have all the ingredients to calculate the body travel within the atmosphere. The change in elevation is h, that is the thickness of the atmosphere. And since the angle gamma is not changing, we will see it later, the traveled space s is h divided by sine gamma, that is 335 kilometers. And this is an arc of a spiral. Its projection onto the Earth's surface is 320 kilometers, and this is an arc of a circle. The angle among the starting and the arrival position we can easily calculate alpha, and it is 2.86 degrees. And then we need to find this landing position as a vector. What we know is the starting and the arrival radius as modulus, RE and RA respectively. Then we know the scalar product among them, since we know the angle alpha in between, just calculated in the previous slide. We know also the cross product, being its modulus, this expression, also with the alpha angle, and then we have the direction given by the n versor, defining the plane of the motion. But n is also known because it is the cross product between the r3 and the velocity relative, and then normalized. Finally, we need to solve a linear system where two rows are coming from the equations C and one from the equation B. Reason why we cannot take all the three equations from C is that those are not linear independent. By solving the system, we have the wanted R4 in vectorial form. Its modulus is the radius of the Earth, so 6,378 kilometers. And if we approximate the Earth as a sphere, actually is not, we may use a simplified expression for longitude and latitude, here above displayed. The error for the purpose of this presentation is negligible, however, and the body is falling into the sea in the position displayed in the map. What we still don't know is what is the velocity, how much time, and in which condition the body is hitting the Earth. And for answering this question, we develop the motion equation. The motion is one-dimensional because there is only one relevant force, the drag, acting in the same direction of the speed. The gravity force is much smaller and cannot deviate the speed direction, therefore it will be neglected, as well as the other inertial forces, centrifugal and Coriolis. We can write now the first cardinal equation projected along the motion direction, defined by the angle gamma, as per picture. Mass times acceleration is equal to the drag with a negative sign, because it's opposite to the speed. And the drag has an expression taken from the aerodynamics, that is half of air density times drag coefficient CD, the cross area A, and velocity square. By introducing the coefficient K, which is so defined, we can get a more compact expression. And for a sphere, K does not depend upon the dimension of the body. For the air density, we assume the exponential model, where ρ0 is the density at sea level and hs is a constant. Then we introduce a second equation. The power generated by the friction, F times velocity, is equal to the mass loss over the time into the ablation heat h. By introducing the coefficient sigma, we obtain this form. The altitude h and displacement s are linked together by a linear relation, and so by derivation we can get another relation between h and time. Now we see how the size of the body is changing. Actually, the drug is generating a lot of heat, and that makes the body consumed little by little. The energy needed for the ablation we have seen before. It is H, being sigma the inverse. If we merge equations 1 and 2, we obtain a simple expression between M and V, whose analytical solution can be found. This is equation number 4. Moreover, from the equations 1 and 3, we can eliminate the time, and replacing the mass expression just found, we get our final differential equation, where V point is only a function of V and H. Important to resume the assumptions of the ablation model. Sigma and K are kept constant. That means the material is homogeneous and the body is conserving its shape while burning. Finally, we can solve our differential equation by replacing the derivative with a finite difference, like displayed for the generic step I. In the first step 0, we are plugging in the initial conditions, and we find the velocity at the following step 1. Then we have also the new height, the corresponding time, and we can calculate the new mass by means of the exponential formula. When all the values of the step 1 are known, we can calculate the step 2 using the same procedure, and so on. The iterations are stopped either if the height becomes 0, we hit the ground, or if the mass becomes 0, the body is burnt out. However, the mass cannot turn into 0 since of the exponential function, but we can assume the body is destroyed when it remains a small percentage of the initial mass. Let's run our example now. We apply the starting conditions found at slide number 6. Velocity and gamma angle are given. We start from a height of 100 kilometers, choosing a step of 100 meters. And now we assume the size and material of the asteroid. Radius 10 meter, drag coefficient 0.3, this comes from the shape and from the Reynolds number. And for the material density, we take 3700, typical for meteors. Sigma is coming from the literature. And since the body is a sphere, we do not need to input K, it can be calculated. We represent here in a table the numerical integration. In the first row, there are the initial conditions. We stop the process at the ground level, where the body has a residual mass of about 54%. The descent time is 28.7 seconds. The velocity drops, but not much. The corresponding kinetic energy is 4.78 into 10 to 5 gigajoule, that is 114 kiloton. Despite of the mass loss, the asteroid is still big, 16 meters in diameter. We will see later what is the effect of such an impact. On the right side, we have a chart of the mass and velocity over the height, and below the height versus time, the red curve, which is almost linear because the velocity changes little, and acceleration increases exponentially, the blue curve. We want to run now a what-if analysis. What happens if the initial conditions or body size change? Should be the body of same material but just 0.5 meter in radius, then it will be completely destroyed when touching the ground. Should be the material of less density, let's say 2500 kg per cubic meter, then even a 1 meter radius body will be destroyed. What about the gamma angle? If the gamma angle is much flatter, for instance 5 degrees, then the same body of our simulation will be consumed significantly more. Should be the angle much deeper, 60 degrees, then the body will reach the ground with the bigger residual mass. If the velocity changes, for example 17 km per second, then also an asteroid of 5 meters in radius gets burnt completely. And here we have also a very big acceleration, so maybe it gets destroyed even before. Let's see now what happened at Chelyabinsk in Russia in 2013. We have here the meteor data and all the relevant parameters. We can run our simulation and we find that the body that is as big as the one of our example gets totally lost before hitting the ground at an altitude of about 18 kilometers. Moreover, its velocity changes up to 12.9 kilometers per second. And below we can see a chart of such a path, which practically confirms our study with some deviations. Here we see a simulation of the body when falling into the ocean. Actually, we have only a big splash, much water gets vaporized, but no tsunami. For that, a much bigger asteroid is needed. Therefore, the impact is not very dangerous if at sufficient distance from the event. If the meteor is falling into the ground instead, that is not the case of our example, the event is much more disastrous. Let's see here an empiric formula to estimate the size of the crater. Its diameter d depends upon the density of the impactor, ρi, the density of the target, ρt, the diameter of the impactor, di, and the kinetic energy with its angle gamma. By plugging in the values of our example, assuming 1500 the density of the target, so the density of the ground, and remembering the final diameter of our body is 16.29 meters, we find a diameter of the crater 743 meters. And by another empiric formula, also from the same author, we can estimate the maximum depth, about 200 meters. For comparison purpose, the Barringer crater in Arizona has a diameter of 1,200 meters.
I thank you for your attention and I hope you have appreciated my effort. Remember that what has been told here has not a general validity, but is just a simulation under the assumptions of the slide number 9. My task here was just to teach you a method. Therefore, you can apply it to different boundary conditions, both for velocity and for material of the impactor. Nowadays, it is extremely difficult to predict if, when, and where a celestial body will hit the Earth, because the event is much sensitive to the body mass and geometry, which are extremely difficult to be determined from far away. Therefore, see you again. Bye bye.